Hi, I'm Jing, and my partner is Yu Shi. So we are presenting our final project of our secret of secure messaging and gaming. Here is our agenda. So first, we introduce the background of our project and the best methodologies of secure messaging and our model and approach, along with our sample code. And finally, is our alternatives to the project and some takeaways. First, why secure messaging? Remember, nowadays we are all communicating with our peers 24 hours, 7 days. However, our message or travels through multiple routers and on the internet, and anyone who get access to the routers can be able to read and utilize our message, sometimes in an illegal way. So, how to do a secure messaging? First, the general methodology is to establish a shared secret with which we can encrypt our message, and our peers can decrypt the peer messages according to the shared secret. It all sounds very simple. However, how to establish and transfer the shared secret so that only us and our peer members can get access to? The secret is mixing secret information with public information in a mathematically irreversible way, which is borrowed from McCormick book. To illustrate this concept, I utilized the famous paint mixing trick. So, for instance, Alice and Bob in a paint class, they start with a common paint and they mix it with their secret colors, which only they themselves know it. And they mix them up and come up with the public private colors, with which they transfer to each other. Then when they get their peers' color, they then mix it with their secret color. Then eventually, magically, they all come up with the common secret color, which only two of them know it. So apply the same methodology to the our chatting system. The common paint becomes a key. So Alice and Bob are starting with the public key and use some one-way manipulation. They can come up with their public private key with the by combining the public key and private key, which they then transfer to the other counterparty. And when they receive the other party's public key, they can use it with their secret key to come up with the share key to decrypt the message. The one-way manipulation we utilize in our model is the Diffie-Hellman key exchange protocol, which is published in 1976. The core of the model is the discrete exponentiation formulation, which is made of three components: base, clock size, private number. And to compute public-private numbers that we transfer to our counterparty, we use the following mathematical formulation. To come up with the shared numbers that we use to decrypt and encrypt our message, we then use the second line. The main difficulty of the model is first how to choose base and clock size. According to the formulation, clock size must be a prime number, so it has no divisions other than 1 itself, and the base must be a primitive root of the clock size, so that powers of the base eventually cycles through every possible value on the clock. And we see previously it was one-to-one setting. How to expand it to group setting? In our case, we assume that all group members share the same group private key. Okay, after discussed the main methodology and techniques behind the secure messaging, we come up with our own toy model. The main challenge is we need to figure out who needs what keys and where are they. Let's assume like I'm chatting with someone in a group chat. So I'm both a sender and a group member. So I need both my private key and public key to encrypt my message. And also I need a group private key and public key to decrypt my peer messages. Here's the sample code. First is the prime module that we use to generate random prime numbers and primitive roots. Then we modify the chat groups module so that it can take inputs as public keys and clock and we build two additional key dictionaries to store the public and private keys for the group. And also, whenever a new group is built, a private key is generated randomly. And also, we build two functions for it to make it easy to get group public and private keys. For the chat server side, we first guess the randomized public clock and base. Then we build a modified exchange function so that when people send messages, they can also send their public key along with the message, so that peer can decrypt their message. And also, we build a new function called exchange key dictionary that whenever I'm connected here like this, or people connect me, I can retrieve my keys immediately from the dictionary. And when chatting, I can use the group key that come with the group peer message to decrypt and encrypt my message. Okay. After discuss our model, there's also some alternatives and that we can improve to better our model. For instance, we can try other encryption decryption methods, and because time is limited, we only apply the simple encryption method that we have discussed in class. And secondly, how to make it more secure. For instance, group public-private keys can change whenever a new group member joins. And also, we can change the clock size so that it can be several hundred digits long, so that people cannot, enumerate all the possible values from the mathematics formulations.
Okay, that's all for the secure messaging part. Next, I'll talk about the game. We incorporate the new game function in our chat system. This is how our tic-tac-toe game works. First, after Pierre and I connect in the game, each of us will first roll a dice to determine who goes first in the game. Then the game starts. Each of us will take turns to take a position in the grid by entering a number between 1 and 9, which you can see in the right. Possible results of the games are either I win, or Pierce win, or it's a tie. After one game is completed, the system will ask whether the players want to play again. Here's some code. We have a new gaming class where we initiate the board, we update the board, we determine who's the winner or whether it's a tie, and then we incorporate it into the chat system. So here it shows how to connect connect Piers and I in a game. This is how they roll dice and determine who goes first. And this is how they make a move and update the board and send the information to the peer. This is they determine whether they want to play again. So let's watch a live demo of the game. So in the left we have Rose, and in the right we have Jean. And Jean wants to play a game with Rose. So they enter D to roll a die. Jean got 4 and Rose got 6, so Rose goes first. Rose choose 1, Jean choose 2, Rose choose 3. And if Jean choose 3 again, but that position is already taken by Rose, so that's invalid input, so Jean have to choose another 5, 6, 7. So here we can see Rose wins, and they can enter Y or N to determine whether they want to play again. So they want to play again. So roll a dice. So this time, Rose goes first. So this time is a tie, and they want to quit the game.
Okay, after seeing our live demo, here comes the main takeaway from this project. First of all, is we need to learn more math because we can see that the core of the secure messaging model is the one-way mathematically irreversible manipulation. So to establish the private public key so that only us and our peers can get access to the shared secret. And also a side story to the project is like Diffie-Hellman that we mentioned before is actually not the first one who invented the protocol. Actually, British mathematicians in the Britain intelligence government already developed something similar to it. However, it was classified as high secret at that time, so people didn't know it until very later. So yeah, very solid math foundation is very important to get started in making our communication more secure and more fun. Thank you. Thanks for
Thank
listening.
you.